Like let them know about the switches when we get back. I don't know why.
Okay, so it's 9:30 and we can get started. So I'm just going to I'm just activating your poll right now. Yeah. All right. Hello. Okay. So you guys read about combinational components, right? So I think with what you read up to, you don't have any new reading until next Friday, because we're going to be talking about combinational components for 2 lectures. And one of the lectures, or I believe probably Monday, I'll be talking more about your lab. So next reading, I believe, is due Friday. But again, do check Canvas to double check me. And the other thing is we have quiz 1 on Monday, right? And homework 1 has been released for a couple days. And quiz 1 and homework 1 are covering the same topics. So let's do, right now homework 1 is due on Wednesday. And the way I'm kind of viewing it is that homework 1 is like a take-home quiz. Quiz 1 is like the quiz in class. But it's covering the same concepts, and they might have a little bit different coverage because they're short. Right? Your quiz, you're only getting 25 minutes for. So if we want to do it a different way, we can change as we go. Okay? So multiplexers. So what does a multiplexer do? Two inputs, one output. What is it doing between the two inputs?
Selects which one to send.
Yeah, it's just a selector, right? It's, am I going to select the first input or the second input? And this is the digital logic circuit for it. And we have the truth table down here. Right? So if S is 0, like is shown here, then that means that our output will become D0. Right? It just matches. And then if S is 1, our output is D1. So we're just selecting between two input signals. And we can look at the combinational logic equation here. So if S is 0, then this one, this becomes a 1, this is a 0, right? So if you OR 0, basically you just become what you are, right? And then if you AND 1, you again just become what you are. So our result is D0. And then if S is 1, this becomes 0. Again, if you OR 0, you just become what you are. And then AND 1, you again are just what you are. So we get D1. Make sense? And then if you wanted multiple bits, you can just instantiate multiple of these. Right? One for the first bit, another for the second bit, another for the third bit, another for the fourth bit, and so on. So we're all good with a 2-to-1 multiplexer? Okay. So the next piece we need to look at is a little bit more details about the 2-to-1 multiplexer. So I'm going to draw the truth table for this fully. So the other one was a little bit simplified. So we have S as our selector, D0 as our first input, D1 as our second input, and then we have Y as the output, right? So again, we're going to write down all of these combinations. And then our output, we can just look at here. So if we're 0, right, we need to be D0. So 0, 0, 1, 1. And then if we're 1, we need to be D1. So 0, 1, 0, 1. And then the way that we get to the simplified truth table is we notice here S0. And let me just change colors. D0, D0, right? And again, if S1 is 1, D1, D1. So this simplifies very neatly into D0, D1, and we can draw this again as S and Y. If we're 0, we get D0. If we're 1, D1. And that is where this simple minimal two-level logic equation can be derived. So if we're 0, we want D0. If we're 1, we want D1. And you can also get to this same equation by drawing the K-map. We see this? Okay. So the thing that we want to see is we want to take advantage of this pattern. So if we scale up, now we want to select from 4 inputs. So a 4 to 1 mux. Then we're going to do the same thing. And one thing I'm going to amend here is to make it simple for us. I want this one to be the higher bits, this one to be the lower bits.
Just,
Mhm.
Can you go back to the
Mhm.
equation?
So now we want to see that when our 2 bits are representing 0, we want to select D0. When our 2 bits are representing 1, we are selecting D1. When the 2 bits are representing 2, we are selecting D2. And then when they are representing 3, we want D3. Right? So if we wanted to write out the equation for this, we again just have to scale up, right? So S1, SO, DO. What do I need S1 and SO to be? If I want to select D0, right? They just need to be 0, 0. S1, S0, D1. What do I need them to be? So S1 is
0.
and S0 is, right? So we leave it alone. And again, S1, S0, and D2. So what do I need S1 to be? S0 is. And then finally, S1, S0, D3. S1 should be S0 should be.
Is you switching them just preference? The
It just makes it simpler because of how I can say that this represents 0, 1, 2, and 3. And that's usually the standard form. Yes. Uh, 2-to-1 mux is this one. Yeah, so 2 bits is instantiating 2 of these. 1 for the first bit, 1 for the second bit. Make sense? Okay. Okay. So the other thing that we want to do is, oh, and I just wanted to mention, like, you can scale this up, right? So if you wanted now an 8-to-1 mux, you just write out the same equation. It is the minimal equation. You would write out your 3 bits that you need. And then when they are all 0, representing 0, then you put D0. Okay. So you just need to put the binary representation, and then what is the output that should go with that binary representation. So if it was flipped, you could still do it the flipped way. It's just not as you wouldn't match. These two are just flipped. Okay. So the binary representation of 1 actually would correspond to D2, whereas the binary representation of 2 would correspond to D1. But it's still just a 4-to-1 mux. All right. So the next bit is I want to show you how to create larger muxes with smaller muxes as building blocks. And this concept is very similar to other combinational components too. So say we have a 2-to-1 mux, and this is how you draw a mux in general. And we want to build a 4-to-1. So the first thing you're going to do is put the 2 muxes here. And now I have, if I'm 4-to-1, I have D0, D1, D2, D3, right? And now I've reduced it to 2 outputs, but then I need to reduce it one more time to 1 output. And now from the outside, if you look at it like a box, this is a 4-to-1 mux. Do you see this? And we just need 2 selector bits. So S1, S0. And the only thing that you need to remember is the lower bits go to the leftmost mux. And the higher bits go to the rightmost mux. And then we can just go through this to make sure. So if S0 and S1, say it's 0, 0, right? So if it's 0, the top one, I am choosing D0, right? The bottom one, I am choosing D2. And then S1 is 0. So I'm choosing the top one. Okay. So 0, 0, I get D0. Okay. If it's 0, 1, then I would have chosen D1 here and D3 here. And then D1 would have been chosen up here. I can swap to the laser pointer. If this was 1, 0, That's not what I wanted. Yeah, 1, 0. Let's do 1, 0. So if we're 1, 0, then up here, I can choose D0, and this one I choose D2, right? But then when I'm at this mux, I choose the bottom one, and that corresponds to D2. And then 1, 1, again, I'm going to choose bottom, bottom. But when I get here, because of this selector bits, I'm going to choose D3. So we've implemented a 4-to-1 mux with 1, 2, 3, 2-to-1 muxes. Yeah. 0. Okay, here. Let's just go through the example with the colors. I just need to redraw this a little bit. It's the wrong color, it didn't select. Okay, so you want 0, 1?
Yeah.
Okay, so S0 is 0. I mean, S0 is 1, right? So we select this, and we select this, right? And then S1 is 0, so we select the top one. So we end up with D1. D3 was selected at first, but it gets rejected here. Any other question? Okay, and we can do the same thing to scale up further, right? So if you have 3 4-to-1 muxes, you can connect them in the same way to make an 8-to-1 mux. Okay. So the next component is a decoder. And again, decoders are relatively simple. We're going from a smaller bit input and decoding it into a larger bit width output. And the simplest decoder is just changing the binary representation over here to creating the 1 bit that corresponds to that on the output. So like if A0, A1 and A0 are 0, D0 is 1. Right? A1 is 0, A0 is 1. That corresponds to 1. D1 is the one that's 1. A1 is 1, A0 is 0. That corresponds to 2. So D2 is the one that's 1. 1, 1 gives me D3. Yeah.
So we're going 1 to 4 instead of 0 to 3 on the outputs.
It's 0 to 3, right? So 0, 0 represents 0. So it is the first one, but it is labeled as D0.
Oh, you're saying D0 is 0.
Yeah,
Okay.
not 0, but 1.
Oh, okay, got it.
Yeah.
Well, I mean, it is the binary of 1, but we're saying that it's the number 0. I'm confused.
So A1 and A0 are 0. This is binary 0, right? So the first bit of output, the rightmost bit, we're going to be putting as the 1. Or if you're 0 array indexed, the 0th bit, right? Is that better?
Yeah.
Okay. And then,
Oh, I was gonna say, so it's the output of, depending on what the A0 and A1 are.
Mhm.
Okay.
Yeah. So A0, A1 is 0, 1, 2, 3. Right? So we get 0, 1, 2, 3. And then again, the implementation of this logic is fairly simple. We can just look at all of these outputs as their own K-map. And we can see that it's very simple to write it as the minimal logic because it's just one min term in the equation, right? So this one implicant is also a prime implicant, and it's also the only essential prime implicant, right? We look at it like this and ignore all this. We have A0, and A1. So the only way to get this as 1 is if A1 is 0, A0 is 0. Same thing for D1. A1 is 0, so it's knotted. A0 is 1. D2, A1 is 1, A0 is 0. D3, A1 is 1, A0 is 1. And again, we can just look at this as the binary representation of the input A. This is 0, this is 1, this is 2, this is 3. Right? So this is your simplest decoder. But your decoders don't always look like this. Any questions on this decoder though? Okay, question? Uh-huh. Yes. Any other question? And again, this scales up, right? So if you wanted to 3 to 8, you just need to write out the binary representation 0 through 7. And you'd get this output. Yeah.
And how are these useful?
So they are used in, I'll give you the example of operational codes in computer architecture. So one thing that we are given is what address of the register is that we want to access. But we have to then generate so say we have 4 registers, if this is an example. So our address can be 0 through 3. So if we're given the address 3, we need to generate 0, 0, 0, 1 to indicate I want the register at this row. So that's when they're used. That's the one the simplest one is used. And I'll show you what you're going to work on in your lab as well. Is another, so this is basically a decoder. It's just not the simplest form of decoder. So what we have here is 7 segments. So 0, 1, 2, 3, 4, 5, 6. So 0 through 6. And if it's 0, it means it's on. If it's 1, it means it's off. And as you're all familiar with a display like this, right? If you turn certain ones of them off or on, you can display 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also display 0, but it's not shown here, right? At least in this corner. It is shown here. basically all of them are on, right? Except for 6. So this is another example of a decoder. Give me your binary inputs, 0, and I want to display it on this display. Which ones do I need to turn on? Which ones do I need to turn off?
So in this table, 1 means off.
Yes.
Okay.
And you can see it's not the same simple decoder because some of these rows have multiple ones, right? But again, we can implement this, and you will implement this in a very similar way that we just solved the previous equation. So we can just look at it one column at a time, right? So for this segment of the display, it needs to be off when I'm trying to display a 1 or a 4. Okay. So that would correspond to, so let's call this A, right? And input is a 4-bit input. I'm just going to call it I. So I3, I2, I1, I0. So the first case that it needs to be turned off is when it's representing 1, right? So I3 is 0, I2 is 0, I1 is 0, I0 is 1. Do you see this? I don't see as many nodding heads. Okay, now I see nodding heads. Okay, so let's do the second one together, right? So I'm going to write them all out again. I3, I2, I1, I0. What does I3 need to be? I2, I1, I0. Okay. And now we have the Boolean equation to implement the logic to drive segment 0 or segment A, this segment. So we have 1 out of 7 done, right? So we can do another one. We can do B together again. So B is going to be off at 5 and 6, right? So let's do B, I3, I2, I1, I0, I3, I2, I1, I0. And I need this to be 5, I need this to be 6, right? So I3 needs to be, yep, I2, I1, I0. And then for 6, I3 needs to be, what does I3 need to be? I2 needs to be, I1 needs to be, I0 needs to be. And this is our logic to drive segment 1 or B, whatever you want to call it. And then you can do the same for the rest of these segments, right? So that is part of what you need to do for the lab. And we have time. So what I want you to do is write out the equations for this. And then remember to keep in mind that you can work in the sum of products like we were doing, or product of sums. One might be more efficient than the other. Like for 4 or E, there are quite a lot of ones. it might be more efficient to look at the zeros. Right? Yes. Are you talking about like input here? Yeah, so if input is 0, I want to, it means I want to display a 0, right? So the only one that I want to turn off is this segment here. So that's the one that's a 1. Yeah, so zeros mean that it's on, ones mean that it's off. Yeah. It's just how the 7-segment display in the board is expecting behavior. You could just implement it the opposite way and negate your logic at the end. That works too. If you like working with 1 is on, 0 is off. So let's work on making the rest. And you don't have to make them the most efficient. If you wanted them to be the most efficient, you would draw the K-map, right? But we can just do what's very simple and easy to implement, right? So do work on this, and your code for today is 979. And there's 2 questions, but just answer anything for the 2 questions when you're done working on your equations.
For the 0A, we did it here, and this would be the same thing if I considered using numbers from 0 to 6, right? Or would it be too much?
Why do you have 6 bits for inputs?
Are we using number 0 for 6? like 0, 0, 0, 0 all the way to,
Yeah, but for the 7-segment display it can only display 0 through 9, right? So log base 2 of 10, which is the number of combinations. I only need 4 bits to represent
for
that.
any number.
Yeah.
And that's why we,
That's why we have 4 bits.
oh,
So we have 6 segments, so we need 6 bits for outputs. But we only need 4 bits for input.
okay, so it's a 2 to 4,
So it's 4 to 6.
4 to 6.
Yeah.
Okay.
We'll really like implement these as like the switches on the bottom of it. You switch some of them and then make some of them basically. Okay. Yeah. I think also is like yeah, I don't know what it is. You're just looking switching for don't think there's enough arguments.
I think it's only 4, right? Yeah, Washington.
Did you use that?
Don't worry about
I thought two was a good one.
I mean, it's
One is eight, not the two.
yeah.
Like, what are you? The two is modern and very cheap.
Yeah, 2 is, that's like super hot. Because it's like cool.
One is very cheap.
I do complete the survey when you are done, so I know that you are done. Yeah, I think most people are done, but just to double check. If you're still working on this, just raise your hand. Right, so I just want to talk a little bit about another way to implement this in VHDL. That is also very simple. So we have our different input combinations, right? And based on the inputs, our output needs to be this pattern, or it needs to be this pattern based on this input, right? So we can use what type of modeling to make this very simple? Yeah, behavioral. And in behavioral modeling, what would I use? If then or case statement, right? So you can use either one. And you can just assign the binary representation that gives you this bit string pattern for a given input. Or if you want to, you can assign them individually. It's not super important. The only thing that you need to do is make sure that you have all of the requirements to make sure it's still purely combination. So the requirements are there's no edge-based sensitivity on your sensitivity list, and all of your cases are covered. So make sure you have that default case, right? So maybe you make the default case be that it displays not a number, like just some random this one because not all of the combinations are valid numbers, right? Or you can just make the default case just be 0. Just as long as you have a default case, you'll be covering that part. And you shouldn't have a clock for the first part of this, but you would for the second part. But just make sure that you don't have for this driver part in that process, you don't put clock in the sensitivity list.
Would you make your default off? Would you need like, so in this case with the 4 inputs, like we would need like 4 switches just to mess around. Would you need like a 5th switch to say, like, turn on? Because it would recognize the 4 low inputs as a 0, but your default case is it being off. So would you need something to like say, okay, now the clock is on, and then it displays a 0 because it sees or whatever number you have.
No, your default case would just be like basically covering all of these. What I just circled here. So 10 to 16, well, 15, right? Because those are not valid digits that you can display with one segment. So all of those combinations would fall into that default case, and then you just display whatever you want to display. So you can turn it all off. You can make it 0. It's not super important.
So if you flip to those ones, it will just either turn it off or whatever you want.
Yeah, whatever you want,
Okay.
whatever you describe in that default case.
Okay.
Okay, so there's that. And we'll cover how to use this 7-segment display to display numbers with 2 digits next time. And that would also involve a clock because it uses the same driver logic. So you need to share it. And the way that it displays multiple different digits is it turns one off and turns the other one on, and it switches very, very fast. But that is all for here. Oh, I guess there is, because we're reviewing addition, I think. So integer arithmetic. So addition, subtraction, multiplication, division. So that is the reading. But it is review. So you do have a reading. So I don't believe you have a reading for Wednesday. But whatever it is, it's on Canvas. And again, if you have any questions about it, you can post on Piazza, private post, email. Anything.
That's true. So when you try to email you, say, do we need to meet? That's it. I tried to message you, but I couldn't find it. Interface too good.
On Piazza?
Yeah.
So on Piazza, yeah, I'll just show you.
Okay, cool.
Can I also watch?
Yeah, the email I sent you, I meant to put in Piazza, but I couldn't.
So let me just leave the.
Can I get Piazza down? I'm still like.